Okay, answer the following questions about electrochemical sounds. It is observed that when silver metal is placed in aqueous thallium fluoride, TLF, no reaction occurs. When the switch is closed and the cell represented above the voltage is 1.14. So this would be read 1.14. Um, okay, now here's what you need to know. When silver metal is placed in thallium 1 fluoride, what that means, and there's no reaction, what that means is silver cannot kick out thallium. Or in an activity series, thallium is on top of silver in the metal activity series. I'm going to come back and talk about what that means. Um, okay, so then um, I think that's it for this one. All right, next slide. Write the reduction half reaction that occurs in the cell. So basically what happens is, why this is tricky is you guys are used to the standard reduction potentials. And standard reduction potentials are a list from the thing that wants to be potential, sorry. And it's a list in order of the thing that wants to be reduced the most, which you're going to see fluorine is up here, and chlorine, and bromine, and iodine. The nonmetals will be up here. Why? Because reduction potentials, oil rig, oxidation is loss, reduction is gain. It's, of course, fluorine, which has 7 valence electrons, really wants to get, it really wants to be reduced, get an electron, because then it will have an octet. Now, what you'll notice, though, is the metals don't like to be reduced. Metals like to be oxidized. So the metals, you know, like the sodium and the lithium, these metals, actually, I think sodium's over, these metals are at the bottom. And so what you need to know is thallium wants to be, is more active than silver. That's why silver couldn't kick it out. And what that means is that thallium wants, metals are oxidized, to be oxidized. Okay, we're giving them human characteristics, more than silver. But the interesting thing is the standard reduction potentials, it's a list from what wants to be reduced the most to the least. And but the oxidation potentials would be if you flipped it upside down and you looked at it backwards. So basically, what this is telling you is thallium wants to be oxidized more than silver. And another way to see it is silver wants to be reduced more than thallium. So the reduction half reaction is silver ion picks up an electron, because reduction is gain, and turns into silver metal, which has a 0 charge. I think if you look at your reduction potential, you'll see something like this. They would take either of those. Next slide. Write the equation for the overall reaction. So basically, we just said that silver turns into silver metal. Therefore, thallium metal must turn into a thallium ion. And then when you add these together, this would cancel this, and you would have silver plus thallium goes to silver metal plus thallium ion. And you can see, I'm going to switch colors, but silver's charge goes down. It goes from +1 to 0, so that's being reduced. And thallium's goes from 0 to +1. Its charge is going up. So thallium is oxidized and silver is reduced. Okay, what's the anode? Remember anox, red cat. Oxidation occurs at the anode. Oxidation occurs at the anode. The anode, they want to know the anode. What's oxidized? Thallium. The metal is the anode. And so what is the anode? And the anode is thallium. And oxidation occurs at the anode. Next question. On the diagram, use the arrow to clearly indicate the flow of electrons. So let's go back to the diagram. This is the way they flow. They flow this way because the electrons leave the thallium and then they come down and they run on the surface of the metal. And on this interface where the metal hits the silver metal hits the silver in solution, the electron combines with the silver ion in solution and makes silver metal. So that's the flow of the electrons. I went a little crazy, drew a lot of arrows. Calculate the standard reduction potential. So this is kind of interesting. We know that the E of the cell is the E of the reduction plus the E of the oxidation. And what's interesting about this problem is this is not on the list that they got on the AP exam. So this is 1.14 volts. They gave you that. This you look up, and this is 0.80 volts. And then this is X. And so when you do this, you get X is 0.34 volts, but we're not done yet. That's what E of oxidation is, but it asks for the reduction potential. So when this is oxidized, when it's oxidized, it's 0.34. So if it's reduced, the reduction potential would be negative 0.34 volts. Because 0.34 volts is the oxidation potential, but they asked for the reduction potential. F, okay, so you have electrodes of platinum, silver, and nickel, as well as 1 molar solutions of their salts. 3 different electrochemical cells can be constructed using these materials. Identify the 2 metals that when used make an electrochemical cell that would produce the largest cell voltage. So what I did is I just looked them up on the sheet. I'll show you where I got that in a minute. And so what I noticed is nickel, and I put them in order. Nickel plus 2 electrons goes to, nickel ions plus 2 electrons. And here E reduction is negative 0.25 volts. And then silver metal, silver ion goes to silver metal. And here E reduction is 0.80 volts. And then this one they give you, platinum plus 2 electrons goes to platinum metal, and that E reduction is 1.2 volts. So remember, this is reduction potentials. We list them from actually we usually list them largest to smallest. So this wants to be reduced the most. This wants to be reduced the least. If this was a reduction potential, we would actually have written them in reverse order. But which will make the electrochemical cell that has the greatest difference? It would be this one. I mean, that's the greatest difference. That's the absolute smallest, that's the absolute largest. So the one that would give you the largest voltage is the cell made of nickel solution and nickel metal and platinum metal, just because that's the largest difference. I mean, this is a difference of 0.4. this is a difference of, I don't know, 1.05, and then this difference would be 1.45. So that's the biggest difference. And then predict whether platinum will react when it is placed in a 1 molar silver nitrate solution. So the question is, will platinum will it kick silver out of solution? In other words, if that happens, then this would turn into platinum nitrate. Here's another way to do this. And silver, if this single replacement reaction happens, platinum comes in and says, hey, silver, I'm going to kick you out, and I turn into platinum 2 nitrate and silver. Okay, so then, but here's the thing. So platinum is PT, and silver nitrate, silver when it's in a compound is +1, and nitrate is -1, so this is AgNO3. And then this would be PT NO3 2, because platinum is +2, and nitrate is -1, and then silver is Ag, and then because of this 2 here, I need a 2 here and a 2 here. And switching colors, we can see that the platinum is oxidized. Why? Because it goes from 0 to +2. And then the silver is reduced. Why? Because it goes from +1 to 0. And so going back, so silver is reduced. Its reduction potential is, sorry, let me grab the eraser. Its reduction potential is 0.80 volts. And then platinum they gave us. Platinum, however, is being oxidized. And then we would have to double this to get things to balance. But remember, we don't double this because it's an intensive property. It's not dependent on the amount of matter present. Now, if you go back here, they told you in this problem that platinum, when it's reduced, is 1.20 volts. So when platinum is oxidized, sorry, this would be negative 1.20 volts. And if I add these together, you would get 2 silver plus platinum goes to 2 silver plus platinum, 2 platinum, sorry, plus a platinum ion. But E of the cell would be negative 0.40, and this means it won't generate electricity. This is non-spontaneous, and non-spontaneous reactions won't happen, so no. The question is, the question was, if I can get this to go, predict whether platinum will react, and our prediction is no, it won't react. E of the cell is negative 0.40 volts, so the reaction is non-spontaneous.